as we talked about back in Unit 1, AP Calculus BC covers everything you learned last year. That is half of the material on the BC test. And then there's new things as well. So the next two units, both Units 2 and Unit 3, are going to be a review of what you learned last year in AP Calculus AB. That way, anything you may have forgotten or didn't quite understand last year, hopefully we get straightened out, because all of this material will be on your AP exam. So Unit 2 is mostly what we covered in Semester 1. So chapters 1, 2, 3, and a little bit of chapter 4. So chapter 1 was all about limits, so we're going to start there. Evaluate the following limits. Number 1, ask for the limit as x approaches 3 of 5x squared minus 8x minus 13 over x squared minus 5. So the first thing you always want to do when you evaluate a limit is directly plug the value in for x. So if I plug in 3 for x, I get 9 times 5 minus 8 times 3 minus 13 over 3 squared minus 5. So what do we have here? 21 minus 13 is 8 over 4, which is 2. And if you just get a regular old number, that is your answer. Remember, if you get a number other than 0 divided by 0, that tells you there's a vertical asymptote, so the limit does not exist. And if you get 0 over 0, it almost definitely means there's a hole there, which means you need to simplify in some way to evaluate the limit. So number 2 is the limit as x approaches 2 of 3x squared minus x minus 10 over x squared minus 4. Again, always start by direct substitution. 4 minus 3, or 4 times 3, minus 2 minus 10 gives me 0 on top, and I've got 4 minus 4 on the bottom, so 0 on the bottom. So we probably have a hole at x equals 2. There's a couple different ways you learned how to evaluate this limit. The first way that you learned was to factor. So if we factor the numerator, I would do 3 times negative 10 is negative 30. Numbers that multiply to negative 30 and add up to negative 1 would be negative 6 and positive 5. So we've got 3x squared minus 6x plus 5x minus 10. I could take a 3x out of these first two, leaving me with x minus 2, and a 5 out of these two, leaving me with x minus 2. So factoring the numerator, I get 3x plus 5 and x minus 2. And the bottom is a difference of squares, so we've got x plus 2 times x minus 2. X minus 2's can cancel. And now we can directly substitute, and we no longer have 0 over 0. So here I've got 6 plus 5 over 2 plus 2, 11 over 4. So that was the first way that you learned how to do it. You also later learned about Hopital's rule. When you're in indeterminate form, 0 over 0, you can evaluate the limit by taking the derivative of the top and the derivative of the bottom, and then plugging 2 in for x. So notice I get 11 over 4, same answer. Remember, Hopital's rule only works if you're in indeterminate form. So if you tried to use Hopital's rule on this one, it would not work. It would spit out the incorrect answer. So if you're in indeterminate form, then you can use Hopital's rule. Number 3. As for the limit as x approaches 0 of cosine 2x minus 1 over cosine x minus 1. Plugging in 0 gives me cosine 0, which is 1, minus 1 is 0, over cosine 0 minus 1, 0 over 0. So we do need to evaluate it some way. I can't factor this. Really, the only way you're going to be able to do this one is with Hopital's rule. So we have the limit as x approaches 0. Derivative of cosine of 2x. Derivative of cosine is negative sine of 2x. Chain rule says times the derivative of 2x. Derivative of the bottom is negative sine 2x, or negative sine x. Plug in 0. I still have 0 over 0. So we need to use Hopital's rule again. Derivative of sine of 2x is going to be cosine of 2x times 2. And then I also had this negative 2 out front. That's negative 4 over negative cosine x. Now if I plug in 0, I get cosine of 0, that's 1, times negative 4. Cosine of 0 on the bottom's 1. Negative 4 divided by negative 1 is 4. And number 4, the last of the, oh, I thought it was last of the limits. One more after this. Number 4, as for the limit as x goes to infinity of 7x squared plus x minus 100 over 2x squared minus 5x. Limit as x approaches infinity of 7x squared plus x minus 100 over 2x squared minus 5x. The easiest way to do this one, well, always plug in infinity first. Infinity squared on top, infinity squared on the bottom. Infinity over infinity is also indeterminate form. So you can either use Hopital's rule, which will work, or you can remember the rule. If the degrees are the same on the top and the bottom, to evaluate the limit as x goes to infinity or as x goes to negative infinity, you divide the leading coefficients. So 7 divided by 2, and that's your answer. If the degree is bigger on the top, if that were a 3, now the limit would not exist. And if the degree is bigger on the bottom, then the limit as x approaches plus or minus infinity would be 0. If you don't remember those rules, you can use Hopital's rule. Derivative of the top would be 14x plus 1. Derivative of the bottom would be 4x minus 5. Still infinity over infinity. So derivative of the top would be 14. Derivative of the bottom would be 4. 14 over 4 reduces to 7 over 2. So you get the same answer either way. And the last one here, when you plug in 4 for x, I get 4 minus 4, 0 over root x minus 2. Root 4 is 2, minus 2 is 0. We are in indeterminate form. The first way you learned how to do this was to multiply by the conjugate, which would work. I think Hopital's rule is going to be easier here. Derivative of the top is 1. Rewrite this as x to the 1/2. So the derivative would be 1/2 x to the negative 1/2. Negative exponents get moved. X to the 1/2 on the top. Divided by 1/2, it's the same thing as multiplying by 2 over 1. And now you can plug in 4. So that's pretty much everything you learned last year about limits. Next type of problem is one like this, where we are asked what value of k, sometimes they use c, but most often k, would make the limit exist for this piecewise defined function. So they give us a piecewise function. We need to know what value of k makes the limit exist. So for the limit to exist, the piece coming in from the left and the piece coming in from the right need to be coming into the same y value there. It doesn't matter if this point here has a different y value or the same y value, either one, the limit would exist. So we don't care what's happening at x equals 2 here. All I care about is what's happening on the left side of 2. Plug 2 in here, 4x. And the right side of 2, plug 2 in here, 4x. And I need the left limit and the right limit to have the same function value at 2. So set them equal to each other and then solve. K is -1/2. So that was chapter 1. Chapter 1 was all about limits and continuity. Chapter 2 is all about derivatives. Derivatives, we did the power rule, the product rule, the quotient rule, the chain rule, implicit differentiation, as well as related rates. So we're going to review that here today as well. Number 8, each of these is asking us to find dy dx, find the derivative of y. So number 8, y equals tangent cubed of 4x minus 1. I'm going to rewrite that as tangent 4x minus 1, all cubed. Those two things mean the same thing. So to take the derivative of something to the third power, we move the 3 out front, drop the power by 1, times the derivative of the inside. So to take the derivative of tangent of 4x minus 1, derivative of tangent is secant squared times the derivative of the inside. Derivative of 4x minus 1 is 4. So the answer here is 3 times 4, so 12 tangent squared 4x minus 1 secant squared 4x minus 1. And I suppose you could write those in terms of sine and cosine, see if anything cancels out, or if you could rewrite it a different way. I'd leave it like that. Number 9 appears to be a quotient rule problem. Y equals 5x squared minus 3 over 2x plus 1. So quotient rule, to get the derivative, it is low d high, so bottom 2x plus 1, times the derivative of the top, minus high d low, derivative of the bottom is 2, square the bottom, and away you go. That was bad. Distribute and combine up like terms on the top, and you're there. So we've got 20x squared plus 10x minus 10x squared plus 6. Quick quotient rule review. And the last of these type of problems has x and y on the same side. X and y on the same side. These are called implicit differentiation problems. Implicit differentiation. So this equation is implicitly defined because it's not y equals something. We do them the same way for the most part, but anytime we take the derivative of a y, we need to use the chain rule and say times dy dx. So derivative of 7x squared y, that's a product. So we're using the product rule. Product rule is the derivative of the first one times the second one plus the first one times the derivative of the second one. The derivative of y is dy dx. To get the derivative of -3 cosine 2y, got cosine 2y. Derivative of cosine is negative sine, so that's going to change that to a plus sine 2y times the derivative of 2y. Derivative of 2y is 2 dy dx. Derivative of this side is 5. Anything that has a dy dx in it goes on one side, so I'm going to leave this over here. 3 times 2 is 6. And I'm going to move that 14xy to the other side. Anything that does not have a dy dx in it needs to go on the same side. And I do that so then I can factor out this dy dx. And then divide by whatever's right here. So dy dx is equal to 5 minus 14xy over 7x squared plus 6 sine 2y. And we had a related rate problem. I'm actually going to save that one. We'll start with that next time. Have a good day.